Hey, good morning, AP Computer Science. I am unable to be in class today. I had some dental surgery on Thursday and still having some trouble. Can't quite eat yet. It took me a half an hour to eat a piece of bread, so I'm gonna take the day off. Hope you don't mind. Don't want to slow down the course though, so here we are talking about number systems. It's going to be phenomenal. So let's get started. First off, just what you need to know in terms of the exam. You need to know about the decimal, which is base 10, what you already know, binary number system, which is base 2, zeros and ones, and the hexadecimal number system, which is base 16, and looks a little weird, and we'll take a look at that in a bit. And mostly understanding how to convert between the different number systems. So how do you turn a binary number into a hexadecimal or a decimal number into a binary, that kind of stuff. So we'll take a look and see how that goes. Just so you know, there's actually a whole bunch of other reasons why you would want to know about binary that's not on the exam. Things like, how his memory measured, why is a kilobyte, a certain amount, and so on. Um, a round off error is a big topic, and actually that is on the AP exam, and we'll talk about that as, why do certain operations not actually work out correctly? We'll see an example in the future where I'll show you in Java. We'll do some math, and the answer will be wrong. And it'll be like pretty straightforward math that you could have all done on a calculator. And it's because of this thing called round off error. When you have a limited amount of space to store a number, if you have an endlessly repeating number, you might end up having to round it at some point and then lose some information, and that can accumulate over time. This is also the plot line of Superman 2, where Richard Pryor steals all the round off errors from financial transactions and becomes a billionaire, which is hilarious. So there's that's something we'll talk about. Not today, but down the road. And then binary numbers are it just kind of seem like magic at this point, and we won't talk about this today, but why is it that binary numbers make Minecraft work and all these other things? And there's a long but fascinating story behind that we'll talk about soon. I'm not sure when I'll have time to record that video. Might be today. I hope it's today. So look forward to that. I'll put a big notice out, and you can find it when I publish it to Teams. Okay, so here's the different binary. Oh, I guess there's octal in there I included as well. So these are the digits that you're allowed to use within any particular number system. Within binary, it's base 2, so you only have two numbers, 0 and 1. Octal is base 8, similar to hexadecimal in its usage, and it can have 8 different digits, 0 through 7. See the pattern there? Decimal is base 10. You use it every day when you're counting and so on. It has base 10, so you have 10 digits available to you, 0 through 9. And then last but not least, we have hexadecimal, base 16. It has 16 possible digits you could use for any particular digit. But unfortunately, we kind of think of 10, 11, 12 as two-digit numbers. So they've used a letter to represent the quantity 10 as a single digit. So letter A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. So those letters are actually all about representing a quantity that's normally two digits as a single digit. So when you encounter those, just don't freak out. That's just what they mean. Okay. So now that we have that over with, hopefully you see the pattern there, and notice, what are the available digits for each number system. So going on, this is a representation of, I guess, the binary and decimal numbers side by side, going from 0 down to 15. So the first 16 numbers of each of these number systems. And it might be a handy chart to refer back to if you ever get stuck, just kind of, especially for the hexadecimal to binary translation. So take a look at that. In the binary numbers, do you see a interesting pattern? We count as 0, and then 1, and then 1 0, and then 1 1, and then 1 0 0, and then this pattern repeats itself again. And then this whole pattern repeats itself in here as well. So binaries by nature is recursive, and that means like it's a pattern within a pattern, kind of like a tree, right? A tree is made up of branches, but branches are really just smaller trees, and so on. So it's an interesting pattern to take a look at. And we're going to look now and see exactly what do these numbers, like how are they encoded. This is, hopefully you'll generalize how all number systems are encoded as a result, because they're very similar. It's just we change what digits are available to us and what each digit represents. So here is an example of the decimal number system. This is the one you already use, right? This is 654,321. And if I told you that's how much money you had in the bank, then you would know what you could buy roughly. You know, if you're rich or you're poor or somewhere in between. If I told you that's how many ducks were attacking you, you would know whether to be scared or not. And I would be terrified. Uh, and just to go over exactly how it works, I know you already know this, but the rightmost digit represents the ones digit, and then it goes tens, 100s place, thousands place, tens, thousands, and so on. This is stuff my 8-year-olds are learning right now. So, obviously you know it, but notice the pattern. It's called base 10 because 10 to these numbers, these place values, are derived from powers of 10, right? The ones digit is the 1 to the 0. The tens digit is 10 to the 1, and 100 is 10 to the 2, and so on. So each digit represents a different power of 10. The base of these exponents is 10, thus it is base 10. And you could figure out exactly what that number means pretty straightforwardly. You have 1 1, 2 tens, 3 100s, 4 thousands, 5 10,000s, and 6 100,000s. So you could sort of assemble that number without much difficulty. This is all super intuitive to us. We don't even think about these numbers, but that's not true about binary. So let's look at binary. The binary number system, or base 2, is the same concept, except that the base is 2 and we only use digits 0 and 1. So here, for example, this place value is the 1s, same as our previous place value. And then we have the 2's place, the 4's, the 8's, the 16's, and the 32's, and so on. Each one of these values is an increasing power of 2, starting at 2 to the 0, 2 to the 1, 2 to the 2. So if we wanted to assemble this number, then we could add up what numbers we have. So we have 0 ones, we have 1, 2, we have no 4's, but we have an 8, so 8 and 2 is 10. We have no 16's, but we do have a 32, so 32 plus 10 is 42. It's 42, it's the meaning of the universe. If you don't get that joke, you should read more Douglas Adams. And it's also the age I'm turning this year, which I'm super, as a nerd, I'm very excited to be 42. So do check out what is the 42 number to nerds. Anyways, looking at that number and seeing 101010, you would think, I don't know, like if you just didn't know how to convert it, you wouldn't know how many ducks that was, you wouldn't know how many dollars that was. You wouldn't really have an intuitive understanding of it. And you won't. Don't expect to like dream in binary or something like that. That's not our goal. Just being able to convert it and understand how the number is constructed is perfectly sufficient exercise. So that's basically how you would convert a number from binary to base 10, from base 2 to base 10. You just add up what the digits mean, and you're good. Okay, so that's binary to decimal. How about hexadecimal? So this is so gross, right? Each of these is an increasing value of 16. So if you look at this number, you wouldn't know what it means at all. I mean, it's got letters in it. So if you wanted to convert it to decimal, then again, each of these places is a increasingly large value of power of 16. So the first one is our ones column, and then our 16s column, right? 16 to the 0, 16 to the 1. Then our 256 column, which is 16 to the 2. And then, it just gets big after that. You can look at this chart yourself and see that it gets pretty unwieldy. Whoops, sorry. That's, yeah, it's not so great, but you could figure it out, right? I would have no 16s. I would have no ones, 116. I have two 256s. I have three 4096s. I have four, and so on. Like you could add up how much numbers you have to convert that into decimal if you needed to. So that's basically the story there. This is not really what we use hexadecimal for, just so you know. You'll have questions like this maybe, but the main thing for hexadecimal is actually converting between binary and hexadecimal. It'll actually function as a shorthand for long binary numbers. So that's actually its value. This is just an exercise in your understanding of how number systems work. So if you see a question like this, do it, be happy. It's not, I mean, it's a bit challenging because of all the numbers, but don't, that's not really the computer science use of hexadecimal. Here's another example of how do you convert from, I guess, binary to decimal. This number is 1001111, which, again, isn't an intuitive number to us as based in the culture we've grown up in. So you would just add it up, right? So I have 1, I have 2 2s, I have 1 8, and so on. But no 4s and no 32s. And eventually you can just add up all those numbers you have, and apparently that's 155. Hey, while I'm on the slide, I'll just mention that this number here, the 1001111, is 155. It represents the same quantity as 155 does in base 10. So if I told you that's how many dollars you had, or if I told you you have $155 you had, then I'm saying the same thing. So that's just a different way of writing the number. Okay, so what if you want to go from a decimal number to its binary equivalent? So you're starting now with a decimal number. So here's an example of how you would do it with 67. The number 67 in base 10. And notice how they write it. It's 67 and a little subscript 10. If you ever see that, that means this 67 is not a hexadecimal number. It's meant to be a binary number. Or, whatever. Sorry, it's meant to be a decimal number, a base 10 number. Oof, the painkillers are getting to me, folks. So here we go. So we have 67. And then what you're going to do is just divide it by 2 and record the remainders going from right to left. That's the hardest part, is to remember to go from right to left. So 67 divided by 2, it doesn't divide evenly, but you can get 33 remainder 1. So hey, look, there's our remainder. That's the key piece of information. So you take that and you write it at the rightmost side of your binary number. And then you take 33 and you just repeat this step again. So 33 divided by 2, best we can do is 16, remainder 1. So you take that number and put it on the left of your first remainder. And you just kind of build the number. After that, you take 16, you divide it by 2, and that gives you 8 remainder 0, so you put down a 0. 8 divided by 2 is 4, remainder 0, so you record that 0. 4 divided by 4 is 2 remainder 0, so you record that 0. 2 divided by 2 is just 1, remainder 0, so you record that 0. And then 1 divided by 2 is 0, remainder 1. And once you get to 0, remainder 1, you're done. That's it. That's the end. You have written down your number. And you can confirm this if you were to check your work, good old, I don't know what age we were when we learned about checking our work. I have 1 1, I have 1 2, and what is this? 1 2 4 6 8 16 32. Oh wait, I did this wrong. 1 2 4 8 16 32 64. Oh, I did it. Okay, there we go. So we have a 64, 2, and a 1. So that adds up to 67. Oh, it works. It does. It does indeed work. So this is a great, fast way to just, crunch through some sort of decimal number and get its binary equivalent. And we're going to write this algorithm later on in Java. We're going to do a little algorithm, piece of code that will do this translation for us. So does that make sense? I don't know. If it does, great. If not, you might want to try it out a few times. Okay, now we're in the big leagues. Hex, binary to hex. When you're doing this, what you want to do is take your binary number and you want to group it into groups of 4 digits. And you start at the right-hand side. So if it's not divisible by 4, your kind of group or a group that isn't a 4 is going to be on the left-hand side. So make sure you group it starting on this side. So 4, 4, 4, and then try to get 4 here. Can do it, so it's 2. That's okay. So then you can just convert each of these from binary to hexadecimal directly, and then just line them up. Just line them up. That's all you gotta do. Just line them up from one side to the other. So if we start with the 11, it's not 11, it's 1, 1. And in binary, that means 1, 1 and 1, 2. So that means, and you can put the leading zeros on if it helps you think in terms of, 4 digits. So 2 plus a 1 gives us 3. So our first starting digit is a 3. Uh, our next group of 4, 1, 0, 1, 1. So that's a 1, a 2, no 4s, but an 8. So 8 plus 2 plus 1 gives us 11. And a B is how you represent the digit 11 in hexadecimal, right? A is 10, B is 11. So then you write down your B. And here's another number, 0010. So that's just, we just have a 2 here. So we just write down 2. And then 1001, that's 1 and a 8 makes 9. So then you write down your 9. There it is. And that's actually the whole purpose of hexadecimal, to be honest, is just we can write a long binary number in a more condensed form. So instead of writing all these ones and zeros, we write them as a hexadecimal number that's much more contained and easier to work with. But oftentimes when you're like, if you ever had to deal with the hexadecimal of any particular, like the binary of a particular program's code, people usually see that through hexadecimal. You may have heard of hex editors, where people actually go and manipulate the binary of a particular program to like hack the program, or like game modders use this a lot. People that mod games will reverse engineer games and then manipulate the binary to change the code to create new things inside of games. Putting Barney the dinosaur inside of some game that didn't have an editor to allow you to do that. Often is done by manipulating the binary, but they'll usually see it through hexadecimal because it's just so painful to look at all those zeros and ones. So this is an efficient way of writing binary. Honestly, is how you'll experience hex for the most part. All right, what else do we got? Oh, nothing. That's the end of our slideshow. So I do have an assignment for you to check out. So do look over that assignment. It's going to be linked wherever you found this video, and this slideshow is also linked there, so you can look back at it. Good luck on that assignment. I hope it goes well, and we can you can hand it in on Tuesday, I guess, when you see me next. Hopefully, I'll be back. I'm sure I'll be back on Tuesday. Um, what was I gonna say? Oh yeah, if you are as you're doing the assignment, you're welcome to just check the answers, and you can do it digitally because I'm gonna just give you a file. So you might not want to like you don't have to print it out. You can just record the answers on a piece of paper or something and check your answers as you go. Actually, you know what? Don't even bother. Let's not even hand it in. Let's do it as a quiz. So do the questions just for practice, and then you can record it any old way you want. You don't have to make sure you do this or that. You just go through them as practice exercises, figure out how it works, and then be good to go for that quiz on Tuesday. So we'll do a quiz on Tuesday on these operations. Anything that you see in the assignment is fair game for a quiz in on Tuesday. Okay, thanks so much, everybody. I hope you have a great day, and I'll see if I can record the more interesting video about how do binary numbers actually produce something that is a program that makes decisions. AI. How does that make AI? So, stuff like that. That's the most interesting part. Okay, have a good day, AP scholars.